Fourth one? I can get it there, but the audio is not there.
The fingerprint?
Yes, the video is there, but the audio is not there. I will have to post the link. I did not post the link.
Did you finish this one? Did you finish?
No, I think that is just waiting.
Alright. Okay.
Yes. The focus.
Yeah. But can you freeze the focus once you do?
No, it's auto. It's auto. It keeps trying. The moment you erase that, it will again keep trying.
Try to keep it like you get to it and then over it.
Finish reading this code. The only thing I don't understand is from this one, they say they use ask for, but how does this happen?
Just give me something.
Is that yours?
It's mine.
It's mine now. Oh, you can use it.
But people hardly use pencils.
I know, but
Well, I can use the little erasers. Sometimes they get hard a little bit.
yeah.
Okay, let's start. So now that Friday is over, those of you who are here are not going anywhere, or at least won't be able to go anywhere. So that's always good to know. So I was going to talk today, and as you've seen, about tail inequalities, about for randomized algorithms, how to analyze the behavior of an algorithm, not an average, but in some sense the worst case, or close to the worst case. But I thought we might do one little fun exercise. It won't be fun, but it'll be an exercise. It might be fun. Anyone call out a recurrence? That's not the homework. Anything you want. This is an open challenge. Just throw it. Call out a recurrence. Someone put your hand up. Yes.
N to the 5/3 times t of n squared.
Wait, what? So t of n. This?
I'm sorry, I have to be less than 1.
Anyone else? This is your chance to get me. So yes.
T of n is equal to the derivative of t. The derivative of t.
T is a discrete function.
It was just a light joke.
Okay. Actually, it may not be that lame. Can you think for a second? There might be a way to that. It might be like T of x is equal to e to the x or something. T of n is equal to x e to the n. That might actually work. Yes?
Square root of n to the square root of t of n minus.
People are hard. Jeez. Okay, square root of n to the power of what?
Square root of t.
All right. Okay. So, our instructor in his infinite wisdom, I'm only going to give you 10 minutes for this, has given us this recurrence, and we now have to solve it. And he claims it's easy. Oh, it's background material. It's all refresher stuff. You should know this stuff. And you have to do this now. What do we do? I've never seen this before. This is not a planned thing, by the way. In case you know. I didn't go up to either. Where do we start? Yes?
Antilog is square of this.
Pardon me?
Antilog is square of this.
Wait, what? Antilog?
First the square of this.
Take the square of this whole thing?
Yeah.
Okay. So I get T of n is equal to n to the square root of T of n minus 1. Is that what you wanted? Okay, that's fine. That's good. That's okay. We don't have to, it doesn't have to work. We just have to try things. Just throw stuff in it. Yeah.
Let's say we can simplify it by saying like g of n is equal to log of t of n. So we can get that exponent out.
Okay, so g of n is equal to log of t of n. So we get 2 to the g of n is equal to square root of n to the power of, what will it be? Square root of 2 to the g of n minus 1. No, is that right? Yeah.
It wouldn't be 2 to the g of n, would it?
Why not? Because g of n is log of t of n. I'm guessing you don't like that.
Well, if you log both sides on the original equation.
Well, you're doing something different now?
Well,
Okay.
you log both sides and then you substitute g of n after you do the log.
Okay, so take a look. Okay. So log t of n is equal to square root of t of n minus 1 plus half log n. Is that right? No, it's wrong?
That's wrong.
Oh, it's completely wrong.
That's wrong.
Oh my god. We make mistakes. It's terrible. How can we do that? Okay.
Now you can substitute.
Now what am I going to substitute?
G of n equals log of t of n.
But, okay, alright. Do I substitute on the right hand, excuse me, on the right hand side too? I don't know. You tell me. You're the driver, I'm just the fan. What do you want me to do? Some of this is not going well for us. Okay, so yeah, anyway. I mean, I had a thought, if I can share. So my thought is, I don't like this half, I'm going to ignore it. I don't even like the log n, I'm going to ignore it as well. Because, you know, logs, who cares? So let's write down this one. Any better? Not much? Well, let's square it. Is this any better? It is? Who said that? Who said yes? Go ahead. I've solved it now. Why is it better?
Because we have some sort of semblance of something we know.
Well, actually do it.
Well, t of n minus 1, we know how to solve that with an adder.
Well, also what's interesting is that now you can, so in the first expression, in the first expression, I could not even tell whether when I went from tn minus 1 to tn, if my number was increasing or decreasing. Well, I was having a hard time thinking about this. Let's put it that way. Right? Whereas here now, with all these transformations I've done, I mean, okay, I've not got the same records, I've got different records, granted. But I think I have some kind of handle on what's going on. Right? So that I'm taking tn minus 1, it's the log of t of n with a square, but basically it's a log of t of n. Right? Or rather, t of n is 2 to the tn minus 1. Right? Okay, so now I know, okay, so since t of n minus 1 is log-ish of t of n, so t of n is 2 to the ish of tn minus 1, there's some kind of exponential-ish thing happening. No, I'm not making this all up. This is how we think. Okay? In particular, if I rewrote this, I said, log squared logs, what's a few pieces of wood between friends? You know, it's just like, we'll just say log t of n is equal to tn minus 1. Now what would you say? Now could you solve this? So now let's get rid of logs, because who wants logs on the right hand, on the left hand side? That was a terrible, terrible idea. We'll put it back. Okay, so it's not, of course it's not exponential, it's much worse than that. Right? Would this be an exponential? The solution to this would be an exponential? No, it would not. It's much worse.
It would be like an infinite exponential, like 2 to the 2 to the 2 to the 2.
Well, that won't be infinite. Would it be infinite?
I don't know.
Well, no, you tell me, what do you mean? It's right there. Is it infinite? How high is that power of 2's?
So there's only two, it's up to n, yeah.
Yeah, so it's not infinite, it's n.
But it grows.
Sure. Okay, so we know what this reference is. It's a tower of 2's of height n, which is a fairly hideous number. Thank you. But it's still not the solution to our problem. But what it's telling us that our solution is even worse than this. Right? So we've made a whole bunch of changes. So first of all, going from here to here, is that going to increase or decrease the behavior of t of n? What do you think? Is it going to get worse or going to get better?
That transformation makes it better.
The transformation, oh well, I should have said better. I mean, is it going to make tn grow at a faster rate or a slower rate when I remove the square?
Slow. It grows slow.
Grows slower. Why is that? Anyone? Well, anyone who said let's go slow, why is that?
Because you're not squaring.
You're not squaring.
So we said t of n minus 1 is equal to log of t of n.
Yeah.
T of n, we're assuming, is bigger than 1, right?
Yeah.
So then the square of a number bigger than 1 is bigger than the original number, right?
No, that's all well and good, but that doesn't really work exactly right here. So let's see. So what I want to say here is that I'm kind of improvising as I go along, is that we're saying if you take t of n, take its log squared, you get t minus 1. If you take its log, you get a smaller number. And so if you're going backwards, you take t of n. Yeah, so at least to me right now, and I'm not fully sure of what I'm saying, so again, this is all in my head. It seems to me that by doing this, I made it grow faster. So my guess for my answer should be less than a tower of 2's of height. But we've also dropped that log n term, and that seems like it's going to be a problem. Because that's a more direct form of the records. Right? We were saying g of n was something times log n, and we threw it out. So we clearly made it smaller by doing so. Right? And let's forget that half. That half is just going to be annoying. But the log n is going to be a bit of a problem because now so you have one thing that's boosting it down and one thing that's boosting it up. And frankly, at this point of this wonderful homework assignment, I won't even think about this anymore. Like, this is boring. But if we have to soldier on, and I'm not sure how far we can get with this. This is a kind of a tricky one. But let's go as far as we can. So let's see. So what do we have so far? We have a simplified expression. Okay. That we said we know what to do. We don't know what to do if we're not quite sure what to do in this case. We know what to do if it's just a log. So let's think about this for a bit more. Right? So log squared t of n is equal to t of n minus 1. Okay. So we know, okay, so what happens if we put a tower of 2's into this expression here? So let's say we in fact claim that t of n is equal to 2 to the 2 up to n. Okay? So then what is Tn minus 1? Tn minus 1 is equal to 2 to the 2 to the 2 up to n minus 1. And then, sorry? And log t of n would be what? Would be, well, yeah, t would be 2 to the 2 to the 2 to the 2 to the 2 up to n minus 1. And then we'd be squaring it. So clearly, yeah, so t of n is not somehow big enough. Okay, so let's say that another way to do this. Any other thoughts? Anyone? I'm just making up things as I go along, but if you have any thoughts, feel free to chime in.
Can we say that t of n equals 2 to the square root of t to the n minus 1, which shows us that it's smaller?
So the claim now is that t of n is equal to 2 to the square root of t n minus 1. That's an interesting idea. Ooh, I kind of like this one. That's very clever. Because now, if you take log squared of t of n, so you do have a solution here.
Yeah, that's just where that came from.
Sorry?
That's just where that came from.
Yes, very good, very good. So now we have a new candidate for recurrence, and that's right. So this is smaller because this recurrence is now t of n equal to 2 to the square root of t n minus 1. Right? And this could be expanded out. So let's see. So let's try expanding this one out. What does this look like? So then this becomes t of n is equal to 2 to the square root of, what will be 2 to the square root of t n minus 2, right? And this will keep happening, won't it? So this will become progress. Very good. Thank you. And this is clearly slower growing than the previous one. Not by much. They don't really get you much bang for your buck here, but grow them. Good. So now we've actually got to the point where all we have is that pesky log n, right? And the half. But so let's go back. So we had. Okay. So we had g of n. Can someone remember what this was? Like this, right? So I'm going to claim that I'll worry about the half later, because my gut feeling is that the half will just, this thing is growing so fast that half is not going to make much of a huge difference. You might reduce this by, it's going to be some, if I assume my answer is some constant to the some constant to the some constant n times, that half might change that, but it's not going to change the overall structure of what it looks like. So I'm going to ignore that for now. Okay, we can check that later. The main thing is this guy. So now what would happen here? So one way to get rid of this is to say, well, let's put this inside as square root of 2 to the g n minus 1 log squared n. And we can rewrite as that as 2 to the g n minus 1 times, what would it be? 2 to the log n log log n. Because log n times log n is 2 to the log log n. No, is that right? No, that's not right. That's not right. So what I want to do is get that into exponent. So is there a way to do that? Can I get this into an exponent form? Plot squared is equal to 2 to the something. No, it's exactly that. What am I thinking? I'm being silly here. It's log log n, 2 log log n. Right, just by taking logs. So this is gn times 2 times log log n. Okay, so now the question is, can we apply the same trick as before? So we knew how to solve t of n is equal to square root of 2 to the tn minus 1. Can we try to solve t of n is equal to square root of 2 to the t of n minus 1 log log n? Does that same trick?
One plus, right?
Pardon me?
In the exponent of a plus.
It'll be a plus, thank you. Oh, that's even better. Yeah. Can we solve that? Again, this. Since I won't be asking you to prove a theta one for this, you could rewrite this expression based on your sense. So we already have a sense that t minus 1 is pretty darn big. That log log n factor should not be making too much of a difference. There's really no way, right? Because it's such a tiny little number, right? So my guess would be that you could replace this just as an O thing. Just say, okay, instead we're going to solve the recurrence t of n equal to 2 to the square root of, no, sorry, what did I do? Sorry. 2 to the square root of t n minus 1. Instead of log log n, I'll just say 1.1 times that, some constant times that. Because it's not going to be less, it's not going to be much more than that. The log is going to be really small compared to that. This is a gross overestimate, but it'll work. And put this on here. But now we can solve this again. Again, up to some constant, we can solve this. And so without, we haven't, come all the way that we need for an assignment. But starting from here, we've got to a point now where we have a pretty good sense of what this recurrence is going, what this function is going to behave like. It's some kind of tower of 2's, but not as bad as a full tower of 2's because there are squirts in there. But in this case, given that you are looking at tower of 2's, it's like, if you're going to be shot by a machine gun or by a whole hail of bullets, it doesn't really matter at this point. It's still a tower of 2's. You're going to die running the same. And for most problems you will actually ever have to care about, that will be enough. Get a sense of how this function looks, simplify it down, throw things out, and then slowly put them back in one by one. And you'll get a sense of the growth rate of the function. And you will almost never need much more than that for any actual problem you have to solve. Because you're really trying to get a sense, okay, well, what is the behavior of this function? Can I get a sense that this is going to be a good algorithm or not? It's only in class when I say, okay, give me an actual answer and I'll give you points for it. But in reality, you're not going to have to worry about it. And so these kinds of things are the ways in which you go about, and many of you come to my office hours and I've been sort of trying to outline some of these ideas, but you just have to get a sense, the most important thing is to get a sense of what it's doing. And there are many ways to do that by simplification. And then slowly, as you learn more, you learn, like I just learned, okay, a constant factor I can ignore for now. A log factor I can ignore for now. Because something much worse is going on. And that's with experience you get that. Okay? So you may not see right now, how do you get away with just ignoring these things? But it does help. And you will be able to sort of build up a set of tools for doing it. Again, you're not often going to get a recurrence that looks like this. There are algorithms whose constants look like this, but they're very exotic beasts. You don't normally run into them. Most natural algorithms you won't see things like this. Any questions before I go on? I just thought I'd do it just for fun because we've been having a lot of discussions about this. Any question? Yes?
Any ideas on 5B?
No. Well played. But no.
Any directions, maybe tangential or something?
Yes, think.
Yeah, of course.
Sorry, you're not getting anything out of me today. Not now anyway. Alright. Let's continue. We've been seeing a number of different ways of doing randomization. Right? We've seen hashing. We've seen approaches based on sampling. We've seen approaches based on fingerprinting. And all of them have the same property. Right? And we talked about Las Vegas, Monte Carlo algorithms. That the randomized algorithm is going to be probabilistic in its behavior. And that behavior, this probabilistic behavior, is either in the resource usage or correctness. Right? Either it runs correctly and uses a certain amount of resources, time or space that can be a random variable, or it always runs in a certain amount of resources, but its correctness is uncertain. It's also a random variable. Okay? Whether it's successful or not. In either case, the thing that governs the behavior of an algorithm is some kind of random variable. Right? And since it's a random variable, it has a distribution. There's a probability the random variable is something, there's a probability that it's something else, and so on. And of course, if you were to think of a one-dimensional random, you know, and everyone thinks, I guess, of a Gaussian or something like that. It looks like Gaussian, some kind of distribution. And this is the mean. What we talk about today is getting a bit more certainty on the behavior of this algorithm. Right? Our game in this class, it's all about understanding the behavior of algorithms. And when we stop at saying, oh, it's a random variable, and here's your expected value, go away and be happy, it only is one point of information about the behavior of the algorithm. It's what it does on average. And it shouldn't be too hard to convince yourself that this is not enough information to really trust what the algorithm is doing. Because after all, let's say I have two distributions. So this is a measurement of time, let's say. You have an algorithm that's running a certain amount of time. And this is the distribution of the time taken by the algorithm. So you have two algorithms. One algorithm looks like this. Okay? And one algorithm looks like this. And I've drawn this, approximately, of course, but to get to point out that they have the same expected value. So we'll call the first one A, the second one. So you have two algorithmic profiles. Your algorithm designer comes back to you and says, hey, I've got these two algorithms, they both have the same expected running time. So you can choose whichever one you want. Which one would you want of these two? Yes,
It
Daniel?
depends on what you want. Like,
Okay.
if you want consistency, then B is nice. If you want, like, hypothetically really good behavior with high probability, then, like, yeah, A is a gem.
This is true. There's no right answer to this question. It's not as if one is better than the other. If you want consistency and just rock solid performance all the time, well, actually, if you want consistency, you would choose A, not B.
Ah. You're correct.
Right?
But if you want
But if you want the chance of doing well, if you're really, really optimistic and you say, every now and then I want to be able to do really well, then you would choose B. Because B has the chance of doing better. The problem though is that if you just had the expected value, you're not going to know. And by the way, a deterministic algorithm in this space would look something like this, right? Well, modulo page faults and cache misses and stuff might look something like this. Right? It might be fixed. So the question is, to what extent can you get to the deterministic ideal, if you wish, or some kind of very high confidence statements about what the algorithm is doing. And it turns out that in order to do that, you have to understand much more than just the average behavior of the algorithm. You have to understand its behavior in the tails. So we talk about the tail of a distribution, and you may have, okay, and the tails of a distribution, again I'll run on one here, are the ends of this thing, parts here and here, right? So in other words, we know kind of what's happening in the middle. We want to know how the tails are falling off. We want to know if it's decaying very slowly. So there's a reasonable chance it could be really bad or really good. We want to know it falls off very sharply. So like, now this is almost a deterministic algorithm. It has very little variance in its behavior. To understand that, we want to know the tails. And the way we want to understand the tails is of a kind of, it's in a form of a meta statement where we say, what is the probability that the random variable is very, very far from its mean? This kind of question, and there's a whole class of questions of this kind, are called tail bounds, because you're asking about the behavior of the tail of the distribution. And you can express this notion of far away in many ways, and we'll see a couple of them. It doesn't have to be greater than, it could be less than also. But this is a basic sense of the question you want to ask. And the tools we develop to answer these questions are tools we then can I'm going to use mu generally for the mean. Okay. So what it's saying is that if you measure your motion away from the mean in units of the mean, so am I a step 1 factor away from the mean, 2 factors, 3 factors, 4 factors, that becomes increasingly less likely. And the proof for this is basically very trivial. I mean, again, so we talked about this a few lectures ago. Why should this be true? Because if it were not true, intuitively, right? If the probability of being far away from the mean above it was not small, then there'd be too much stuff above the mean. So technically, I should probably put, so let's say, so suppose the probability that x is greater than or equal to a mu is greater than 1 over a. Okay? Then if you look at the total average value, right? It's going to be basically, there's going to be some term. So if you look at the expected value of x, it's going to have 1 things for all values of x less than a times mu. And it's going to have 1 thing for all the things that are above a times mu, right? And remember, x is positive. And we've just shown that this part is going to be greater than mu. Because I just said that, right? Because if I look at the average value of things that are more than a times mu, their value is at least a times mu. So it's at least a times mu times 1 over a, which is mu. And so this number is greater than mu, which is a contradiction. That's the intuition. You obviously cannot have too much stuff too far away from the mean, otherwise your mean would have to move. Does it make sense? So this is the Markov inequality. And what can we do with this? We can do a couple of things with this. They're not so bad. So I'll give you an example of this. So any questions for it? Suppose I have suppose I'm tossing a bunch of coins, right? So I'm going to use this example as a running example. So I have n coins, they're all fair, right? What's the probability of seeing more than 3n over 4 heads. So I toss a fair coin 1,000 times, and I want to know the probability that I'll see more than 750 heads. Okay? Can we apply the Markov inequality to solve this problem? So here's what we can do. So we can define a random variable. So let's say xi is equal to 1 if the ith toss is equal to heads. Okay? So there are n variables like this. What is the total number of heads we see expressed in terms of the xi's? So we were looking for the total number of heads. We're going to examine that quantity, right? How do we express the total number of heads in terms of this variable xi? Xi is 1 if the ith coin tosses heads. So the sum, it's a sum, right? So the total number of heads, we'll get here, 1 second. So the total number of heads is equal to the sum of the xi. Okay. Now we want to know, okay, this is a random variable. This can change. We would like to know various things about it. In particular, we first want to know what its expected value is, because until you have the expected value, you're going to apply the Markov inequality. So what's the expected value of this quantity? So let's call this quantity x. So the expected value of x by linearity of expectation, right, is equal to the sum of the expected values of the xi's. Each xi is 1 if it's heads and 0 if it's tails, and it's a fair coin. What is the expected value of an xi?
1 by 2.
Half, because it's well, probably half it's 1 and probably half it's 0. So this becomes equal to n over 2, right? Because there are n variables. So now we know the expected value of the variable. Check. Is x always positive?
Yes.
Check. We can apply the Markov inequality. Okay. So we want to know the probability that we see more than 3n over 4 heads. Well, if mu is equal to n over 2, and we want a target that's a times mu should be equal to 3n over 4, what is a? A should be equal to 3 halves. Thank you. So the probability by the Markov inequality that we see that x is greater than or equal to 3n over 4 is less than 2/3. So the chance of seeing more than 750 heads if you toss 1,000 coins is less than 2/3 according to the Markov inequality. So, by the way, what do you think of this bound? Do you think this is right? And you think that it's a good, gives you a good sense of the likelihood of seeing 750 heads if you toss 1,000 coins? What do you all think? I mean, it's correct. There's nothing wrong with it. It's a correct bound.
Pretty big bound.
Sorry?
It's a pretty big bound.
When you say big, can you explain?
So 2/3 of the distribution, I don't expect to be in the top quartile of the values.
Correct. You don't expect 2/3 to be the right answer. And so all this is saying that it's less than 2/3.
Right.
We don't know how much less than 2/3 or whether it's 2/3. But you think your intuition is telling you that if it were really 2/3, that seems odd. It seems odd that 2/3 of the time you could see, 1/3 of the time, 2/3 of the time you could see 750 heads. That just seems wrong somehow. And you would be correct in thinking that, because it is not a good bound. It's not a wrong bound, but it's a loose bound. It's a loose bound because we don't know anything about the x's. We haven't assumed anything about them except that x is positive. We haven't even assumed, by the way, that the xi's are positive. We just assume that x is positive. I mean, maybe there's some weirdness going on that allows the x to be positive and the x. We don't. In this case, it worked out, but we're not assuming anything about them. And so, as you will see, as we go through this lecture, as we put in more and more information about where our randomness is coming from, we will hope to get stronger and stronger bounds on what the tails look like. So this is the weakest kind of bound you can get, but it's very useful if you're not quite sure about what's going on. For example, you don't need to know if the xi's are correlated. Why? Hey, linearity of expectation. I don't care. You don't need to know if they have a bounded variance. Why? I'm not using the variance. I don't care. You don't need to know anything about those variables except that they're non-negative. So it's very powerful in that it applies in many places, but it's very weak in that it can't say much because it has to apply across the board. And in fact, you can construct an example where this is tight. You can construct an artificial example of a random variable where the bounds of the Markov inequality, that 1 over a bound, is exactly what you're going to get. And it's not too hard to imagine how that will work. You just basically zero out everything below and keep everything on top, and you have to speak that much. So without any further information about x, we can prove that this inequality cannot get any better. This is the best you can do. And so the question is, what more information can you put in to allow yourself to say something a bit strong? Okay? Is that clear? Well, the first thing, that you might think of is that, well, if my coin tossing was some kind of algorithm running over and over again, I expect that these runs are independent of each other. I expect that that there's no correlation between things. Can independence somehow help me in some way? And thinking about independence, and also thinking about variance, and not just expectation, leads you to the next inequality, which we'll call the Chebyshev inequality. And again, the way to think about these inequalities, they're all little weapons you use depending on what your problem calls for. Okay? All right. So again, just to remember, we know what the variance of a random variable is. The variance of x is equal to the expected value of x squared minus the square of the expectation. And we often use the term sigma equal to the square root of the variance as a standard deviation, or so you can also call this a sigma squared. All right. Now you, of course, had to do something in your homework assignment relating to this. But I will say something here that we know that if x1 to xn are independent, and hopefully you remember what independence means. X1 and x2 are independent if the probability that x1 is equal to something and x2 is equal to something is the same as the independent probabilities of the two things multiplied together. Okay? So they don't really affect each other. And so if x1 and x1 are independent, then their variances okay. So the sigmas don't add, the variances add. And you can okay, having said that, let me now set up the inequality. Assume now that you have a random variable that has a bounded variance. And I'm going to mention this point in a second. I'll come back in a second. Let me just state the bound. So the inequality says this. So again, for any a greater than 0, the probability that x minus mu is greater than or equal to a times sigma is less than or equal to 1 over a squared. This is the inequality. So let's take a second to parse what we're saying here. So again, is this a tail bound? It is, because we are measuring the distance from the mean. We're saying what is the probability that we're far away from the mean. So that's good, it is a tail bound. Notice though that now the unit of measurement is not in terms of steps multiplied by the mean, it's in terms of steps multiplied by the standard deviation. And again, if you've done any class in probability and you look at a Gaussian distribution and you talk about 1 sigma, 2 sigma, 3 sigma, this is why. That it's more natural to measure how probability decays in terms of the variance, because that's what controls the spread, rather than just in terms of the mean. Okay? So this is the unit of measurement. And then once you have the unit of measurement, you look at the probability. So the further you get away from, the more number of units you step off, the lower your probability drops. And the last thing I want you to note is that the previous bound was 1 over a. This is 1 over a squared. Which means what? That means that you're saying something is decaying more rapidly. It's falling off faster. For Markov inequality, decay is like a 1 over a, which is like a sort of a gentle reciprocal thing. This is like a faster reciprocal. Okay. In other words, this is giving you a stronger bound, and the price you have now paid is that assumption, is the bounded variance assumption. So I talk about bounded variance. I don't know if you're familiar, there's a lot of distributions out there, not things like Gaussians, that do not have bounded variance. Which basically means the distributions go off to 0 in the limit, but they don't go off fast enough. The Gaussian distribution drops off exponentially. So it has all finite moments, because an exponential drops off faster than any polynomial. But there are distributions, that are so-called heavy-tail distributions, that show up actually a lot in nature, and they show up a lot when you're dealing with data. They don't fall off exponentially, they fall off very slowly. So you have what's called a long tail, right? This is, it's a marketing term as well, the long tail where you want to market these large enough groups that are rare. And the problem with that big tail is that even though the probability is decreasing, it's not decreasing fast enough, and the magnitude of that value is increasing because you're going off to the infinity. The combination of those two things makes your variance go unbounded. So you can't always apply this inequality, but when you can, you win. Any questions about this? I'm going to give an example now, but before I do that, any questions about the statement of the result and why it's a tail model? Yes?
So it seems that even if you don't know what the variance is, if you know it's bounded by something, you could do the probability of A times that bound of the square root of the variance.
That's correct.
And you can still apply this.
That is correct. If you know the variance is at most 10,
Yeah.
then you can use this bond. It'll be a weak bond, but it'll work. And that's a very good point, that you don't always know the variance, but if you can give an upper bound the variance, this will suffice. A lower bound obviously won't. Yes? Okay. Okay. So let's try to apply this to our running example now. So remember our question. Our question was, what is the probability that you see more than 3 n over 4 heads when you toss 1,000 coins? And notice that I am not going to change the process at all. It's the same process. I'm just putting on a new lens and analyzing the same process, but using more information about the data. Because I'm going to assume now that my coin tosses are independent. So I toss them in a vacuum, there's no dust, there's no whatever. But each coin toss is probably half or one independently of what happened before. Okay? Which is how coin tosses should be. How many of you read that paper where a bunch of mathematicians proved that if you model air velocity and sort of dust and turbulence, the probability of coming up the same time, it's the same surface it started on, is about 51%. It's not exactly a fair point. It's a very interesting paper. Okay. So the proof of Chebyshev's inequality is actually very easy. You use Markov's inequality. In particular, you construct a random variable. So the proof of Chebyshev inequality says let y equal to x minus e of x whole squared. Y is now a positive random variable, right? So you can apply Markov's inequality to y, and that will give you Chebyshev's inequality. I'll let you look at the details. Okay. So let's look at our example. So again, remember that we had the xi, we had x equal to sum of xi. In order to apply Chebyshev inequality, we need to know what the variance of x is now, right? So we say the variance of x is equal to the variance of the sum of xi. And because we now assume they're independent, okay, what's the variance of a single random variable? Well, the variance of xi is equal to e of xi squared minus e of x whole squared. Okay, what is e of xi squared? Xi is a random variable that with probability half takes the value 1 and probability half takes the value 0. Xi squared is a random variable that with probability half takes the value 1 and probability half takes the value 0. So e of xi squared is equal to half. What is the probability of, what is e of x whole squared? We just said the expected value of x is half. So square that is 1/4. So the variance is 1/4. Right? Therefore, the variance of x is equal to n over 4. Right? Because it's sum. The right says sigma squared. Okay? Okay. So, just for convenience, we'll write the Chebyshev bound in a slightly different form. The Chebyshev bound will write as the probability that x minus mu is greater than equal to a is less than equal to sigma squared over a squared. You can see that's the same thing. If you replace a by a sigma, it would cancel out. Okay. So now we can plug in a bound. So we're just going to look at one side of this distribution, side of going above. We're going to look at we're actually going to look at two sides, going above 750 or going below 150, going below 250. So we're going to estimate the probability of something even. We're going to estimate an even larger probability. So this is this is n over 2, and this is going to be n over 4, right? Because we want to get the 3 n over 4. So then this probability is going to be less than or equal to sigma squared, which is n over 4 whole squared divided by n over 4. No, wait. Sorry. What am I doing? Pardon me? Sorry?
Square is just an over.
No, I did something wrong here. Hold on.
Sigma squared is just an over. It's not an over square.
Oh, sorry. Yes, thank you. Devon. Yes. This is an over square. So now what we've got from this is that the probability of seeing more than 750 heads, or in fact, so it's even more, or seeing less than 250 heads, is less than 4 over n. Not 2/3, but 4 over n. And now finally some sanity is returning to this process. Now if n gets larger and larger and larger, you expect this number to become extremely unlikely. Right? You expect it to go to 0 in the limit. Because you expect really high concentration. And so this is immediately what you're getting from using a slightly stronger assumption on your input. Instead of saying that I have a 2/3 bound, so if we write in the Markov bound again, so the Markov bound said the probability of what we're seeing here will be 2/3. The Chebyshev bound is saying no, it's actually going to be 4 over n. This is much stronger. It's a much smaller number, so we're getting a much stronger probability that we know what's going on. A much stronger sense we know what's going on. That make sense? Any questions about that? Yes.
So there might be something trivial I'm missing, but as far as I know, variance is not linear, so why can we pop it out there?
As far as you know, variance is not linear.
Yeah.
Remember what I said.
Even when they're independent.
You disagree?
Yes.
Uh-huh. So you were saying that even if variables are independent, the variances do not add?
Yes.
Because, well, that's not really fair because I know who's making the claim, not you. But can you tell me why you think?
So it's because the probability of a single event happening, so the variance is defined by the summation of the probability of an event times that event minus the mean squared.
Not the probability times the event times the mean squared, the expected value of the square, ex squared minus the square of the mean, right? The variance is the expected value of the square minus the square of the expected value.
Can't it also be rephrased as the other term? Because that's what it's normally defined as.
Well, it's the expected value of the deviation from the mean. That's what you're, yeah. So the variance is the expected value of the square deviation from the mean.
Yes.
Correct. Yes? So,
Okay, I'll trust you.
no, don't trust me. Keep going. Never ever trust me. So you're good. So you have that. And now you have x plus y.
Yeah.
And you're saying, why does this work out? Think about, so I want you to visualize what's going to happen because it will take too long and I'll probably get it wrong to write it. So you have x plus y and you're worried, I think, about cross terms. Because you're saying I have x minus expected value of x whole squared. I have y minus expected value of whole squared. But now I have x plus y minus expected value of x plus y whole squared. And now I can see these cross terms showing up. Okay, remember x and y are independent. So the probability of x and y jointly is the probability of x times the probability of y. That joint probability decouples into two parts. When you do the algebra, it factorizes.
Okay.
That's the intuition. It's not proof, but that's where the correlations are going to go away. And that's why it will add.
Makes sense.
But you'll have to work out the details to see it.
Yeah.
Yes.
I think you may be thinking of standard deviation.
Sorry, can you speak louder?
I think you may be thinking of standard deviation instead of variance, because in that case they don't have.
Isn't variance just standard deviation squared?
Square. Yeah, but that's what. The squares add, but the square roots don't add. So that's possible. I don't know if that was it, but that's the thing there, that the variances can add, which are the squares, but the square roots are not going to add. Even if they're independent. But that's possible. Any other questions? Okay. So we now have two bounds of increasing strength going along with increasing amount of assumption on the input. It turns out that for the vast majority of randomized algorithms that we will work with, or any kind of randomized strategy, we can apply an even stronger assumption, much stronger than this, which gets us a way better bound. And that what leads us to what is called the Chernoff bounds. So I call these the three Russian bounds. You may have also, there are also many different independent reformulations of this. Some of these are called, they're called the Chernoff-Hofting bounds. Something called Bernstein's inequality. I'm writing this down just in case you've heard of any of these and I'm wondering, what's the connection? Then there's, let's see, there's another one that's called McDiarmid's inequality. And there's a whole host of bounds of this kind. There's a whole book on this, in fact, that talks about very strong bounds you can get under independence assumptions of data. Okay? And they all have the same flavor, and we'll see that in a second. If you think of the intuition behind this progressive strength in bounds, for the Markov inequality, we needed to be sure that the variable had a bounded variance, a bounded mean. It had a mean, otherwise it wouldn't have worked. If the mean was unbounded, then you couldn't have applied Markov inequality. For Chebyshev to work, you had to assume bounded variance, because it wouldn't work. Bounded variance, of course, is related to the second moment of a distribution. So the second moment is the expected value of x squared, right, which is the first term of the variance, and you subtract the mean from it, you get this. So you can think of the variance as just kind of a normalized second moment. It's like a centered second moment. There's nothing stopping you from defining higher moments. You can say, what's the expected value of x cubed, x fourth, x fifth, right? And clearly, if your distribution doesn't tail off fast enough, at some point, one of these moments will become unbounded. And your ability to do tail-bound analysis will stop at that point. So in principle, beyond Chebyshev, I could get you a bound. I could write down a certain bound for 3, for 4, for 5, for 6, for 7, and you could appropriate 1 over a cubed, 1 over a to the fourth, 1 over a to the fifth. You get all these bounds. And I could keep going for a while. But rather than spend infinitely long writing these things out, I could just cut to the chase and say, well, what happens if you have all your moments? If every single moment of your distribution is bounded, which is a really strong assumption, but is one that is satisfied by, say, any exponential distribution, for example, because it decays exponentially, faster than any polynomial. If you have that, then you get a much more powerful bound, which tails off even faster, and we're going to say that bound exists. Okay? To prove that bound is a lot harder. So I'm actually not going to prove the bound. I'm going to state it. Firstly, it's a very general form, and then in simplified forms, it'll be more useful in practice. But keep in mind that there are proofs in the notes. They require you to reason about essentially the entire collection of moments of a distribution. Just like with Chebyshev, we said, okay, let's write down y is equal to x minus mu whole squared and apply Markov. Here you write down a much more complicated function called a moment generating function, and then apply Markov to that. And that's how you prove the Chekhov form. So it's not hard, except but you have to learn a lot of machinery about moment generating functions. And that's not something you need to know. You won't need to know this in the class as well, but if you're interested, you can take a look. So let me set up sort of a simple version of this form. Yeah. Okay. So once again, we have these random variables. I'm going to write down explicitly that we have a collection of random variables that are 0, 1. So 0, 1 random variables, that means they're all coin tosses of some kind. And let's assume, just for fun, that they're not even fair coin tosses. So let's say that the probability that xi is equal to 1 is equal to pi. So it doesn't have to be half. Which in particular also means that the expected value of xi is equal to pi. So, what is the bound going to say? So the bound says, let's again compute the sum, which is the thing we care about. So let x be equal to the sum of the xi. And we want to get a tail bound for the behavior of x. Okay. And so the bound we can say is that, so again, the mu, what is the mean of x? What is it going to be? Given all the information I've given you so far, what's the mean of x?
P1 plus P2 plus not to Pn by n.
Not by n. Expectations add. You're already doing the averaging before, right? Because pi itself is an average.
P1 plus P.
Exactly. Because the expected value of xi is pi, and linearity of expectation applies. Okay. So now we're going to say, again, write a tail bound. What is the probability that, and I'm going to write in this form, which is again slightly different. I'm going to go back to using units of the mean. This is going to be less than equal to some constant, which I'm going to subscript with delta, to the power of mu. Where, and you'll see why I did this. I never remember, that's what I keep looking at. I never actually have to use this expression, so I have to look at it to remember what it is. But it's just a hideously frightening expression. So again, before I go into this in any detail, let's try to parse what this is telling us, right? So again, it's a tail bound. It's saying what is the probability that x is far away from mu. You should now think of delta as something like small. Think of delta like 0.1. Because now we have the power with this bound to make very precise statements about deviations from the mean. So think of delta as not a very big number. So what is the probability that I'm within, I'm 1.5 times the mean, 1.6 times the mean. What we're saying is that the probability of this happening is some number that's really small. So you think, again, you should think of this as a really small number that decays exponentially with delta, okay, to the power of mu. And it has to be to the power of mu, but you can, again, pretend mu is 1 for now. Just want to think about this one. I will almost immediately now write down a shorter, more intelligible version of this bound. Okay, but the main thing I want you to take away from this is that you are now again back to measuring with respect distance with respect to the mean. Because of course there's no video, I'm looking at all moments, not just the variance, so I don't have to look at any particular one. But now I'm saying that decay is now exponential. And so let's work this out. So let's say that, let's give you a simpler version of this bound. Yeah. So a somewhat simpler version that you can give, which looks something like this. So again, you have the same setup as before. Probability, and I'm going to make this even slightly different. I'm going to say the probability you deviate from the mean in any direction, above or below, okay, is 2, because there are two sides to this, e to the minus So again, remember, before I had things like 1 over a, then I had 1 over a squared, where a is like delta here. Now I'm having e to the minus. It's a much, much stronger decay rate than getting. Okay? And this is an example of what is called a Chernoff bond. There are many, many different flavors of this. Are your variables 0, 1? Did they take on other values? Are they bounded? There's all kinds of things you can do. But for now, all you need to know is that if you have independent random variables, okay, and you combine them in this way by adding them up, then you are going to get a very, very, very sharp concentration around the mean, which means it is very, very unlikely that you will deviate from the mean by some more than a little bit. And that's the intuition you want to take away, that when you're from an algorithm design process, what this is telling you is that if you have some random process that's variable, and you want to really sharply reduce the variation of the behavior, take an average. We know that already, it's something that's intuitive to us. But these kinds of bounds and the central limit theorem, which are closely related to, are giving you a formal justification for doing that. That the likelihood of deviating from the mean value goes on exponentially as you average the mean. Okay? And so let me give you, again, we'll work through our coin flipping example again, but now with this bound here. Okay? So let's look at the coin flipping example. If you recall, for the let's see. So let's look at again the probability that x minus mu is greater than or equal to n over 4. Just the way we did the previous ones. This basically means that what is delta going to be? Delta is going to be half, right? So if we want to get this bound, we know that mu is equal to n over 2, and so delta is equal to half, if we want to apply the Chernoff bound. We know these are 0, 1 random variables, we know that mean is n over 2, we know they're independent. So if we plug this in, what is the bound we get? We get 2 times e to the minus n over, what is it? N over 2 times 1 over 3 times 1 over 4. Okay. Yeah. So again, let's compare. So our Markov bound gave us this probability of being, this is less than or equal to 2/3. The Chebyshev bound gave the same probability as being 4 over n. And I'm cheating with the Markov bound, it's only one-sided, so it would be even worse if we tried to do anything else. We couldn't do anything else. So that's the Chebyshev bound. And the Chernoff bound, oh, I have to go more than this, gives us 2 times e to the minus. So you've gone from a constant to something that depends on n to something that depends exponentially on n. Okay? And that's the power of these ones. And in particular, you could now ask, right? If you wanted a probability of something like 4 over n or 2 over n, okay, what kind of deviation would you see? So you can ask the question in reverse. You say, okay, I want the probability of deviating to be something like 2 over n. What kind of deviation will I expect to see? It turns out you can show that the probability that x minus the mean is, if it's more than something like square root n log n, has a probability of less than 2, right? Up to some constant. So again, this is something you may have seen before, right? That the deviations from the mean when you're tossing coins behave like square root. The deviations look like square root of n. They work in that unit because that's the square root of the variance. Okay? And so if you look at compare that to a Chebyshev bound, the Chebyshev bound said, oh, well, the probability of having more than 750 is 4 over n. This is a much sharper bound. Square root n is very, very small. You're saying the probability that's more than, I don't know, 35 or something. That's as much. So you're really going to get a sharp concentration around it. Okay? Here's another thing you can do. Another thing you can do is this. We can go back to our load balancing example. So let's look at our load balancing example. So if you recall, we were throwing, we throw n balls in n bins, right? So we said the expected load is equal to 1, but the max load could be something like log n over log n, right? We said that, and we said, oh, if you use the power of 2 choices, you can move this down, but it could be pretty bad. Suppose I said I'm now throw n log n balls in n bins. What is the expected load per bin? So I have n log n balls, I'm throwing them in n bins. What is the expected load I'm going to see per bin? Expected load is easy. It's not a hard question. I have n log n balls, or okay, forget, I have m balls, I have n bins. I throw them in at random. What is the expected load per bin? No, I have m balls, I have n bins. How many will it be? Just m over n. Just divide evenly. So in this particular case, the expected load would be log n. Right? Because I have n log n balls and n bins. But you can ask now, okay, what do you expect? So before, when the expected load was 1, I could see deviations of up to log n. So some bits could get a lot of balls, some could get just 1. What happens in this case? Well, again, it's the same. I just threw more in. You should expect to see more deviation. But you don't. It turns out, and you can apply a Chernoff bound to prove this, is that the probability that the load is more than something like 1.5 log n is very, very small. It'll be something like, something like 1 over n. And not only that, you can also show the probability that the load is less than 0.5 log n is also very, very small. In other words, what the bound is saying is that if you threw n balls into n bins, there wasn't enough concentration in probability to even things out. So you could have these huge skews 1 log n. So you have a distribution that could look like you could have some things here and some things here. But once you throw more balls into the bins, n log n balls, they're all going to be roughly log n. There's going to be small constants, but they're all going to be roughly log n. Things even out. This is the power of it's not the power of the bound. The bound is just a bound. It's not changing the way the algorithm behaves. But what it's telling you is that probability is doing interesting things here. It's concentrating. And if you want to make things reliable and even, repeat them. And the Chernoff bound is the muscle that gets you to even things out. And that's really the main intuition I want you to take away from this lecture. It's a lot of, grunging through probability. But what it's giving you is insight. It's telling you that there are these exponential behaviors that are to your advantage. When I say things like, oh, just repeat this log n times, I am using a Chernoff bound. Because a log n in the exponent allows me to get a huge benefit. I couldn't do that with any of my weaker bounds. Okay. Yes?
The expected load is log n. How are you saying that things are evening out? I'm not able to catch that.
Everyone's getting more load, but when they look around, they're not that unhappy. Is what I'm trying to say.
Okay.
So if you want to give people the same amount of work, give them lots of extra work. That's what you're thinking about it. But the claim is that, okay, so the argument is that, and it's, I'm lying a little bit in this whole argument, but the idea is that once you have enough trials, in this case balls being thrown into bins, the effects of what are called concentration kick in, and you start regressing to the mean, which is log n. And you regress more tightly to the mean. See, any random variable, it has a distribution, has a mean, has variance around the mean. We know that. But if you take a bunch of that random variable and add them all up and average them out, the way it cannot deviate from the mean too much anymore, because the deviations cancel out. So all you get is the mean, you get much more concentration. So over time, right? So if you take, and you could easily do, if you look at a sample of values, right? You take, you take a process where you take a coin, you toss it 10 times, take the value, write it down. Or take a dice, roll it, get the distribution of values, right? So you get some distribution of values from 2 to 12, right? But now you take the same die, you roll it 10 times, take the average, write that number down, and now record those values. The next step is going to look like this. Now take the same die, roll it 100 times, take the average, and do that a bunch of times and look at the plot you get. That number is going to look like this. Where this, in all cases, this is the mean. This is 7. Right? And so what's happening with repetition is that your distribution is getting more and more concentrated around the expected value. And that allows you to become, in some sense, more deterministic. Because the deterministic ideal is a single straight line. And so when we want to make randomized algorithms more reliable, the way to do that is to repeat and take averages and other tricks like that. So there's a whole industry of how to make randomization better, how to make the probability of error smaller, either by blind repetition, which actually could be expensive because you have to do this a number of times, or by being even more clever about how you do the repetition. So there's a lot of work when you start, and I'll be talking about this on Thursday. When you start looking at your project papers, you'll start encountering things like this all the time. You'll start seeing people say, "Oh, we just apply a Chernoff bound," and this is why they're doing it. Because they want to be able to get these things to be very precise and very predictable. Okay. Yeah.
Is this what we were trying to do with Monte Carlo?
When we repeat it?
Yeah.
Yes. We could use a simpler argument there. Because we're just trying to say, okay, the probability of success is 1 over n choose 2. We repeat this n choose 2 times, where we're using a simple version of this argument. We didn't need the full power of a Chernoff bound. But you could analyze that method using this and get the same answer, because they're independent trials. Yes?
Can I have some information on what sorts of distributions satisfy the requirements of the...
It's a very good question, and there's been a lot of study of this. For example, I talked about independence, right? All the variables need to be completely independent. That's not entirely true. If you have some limited k-wise independence for k, something like log n, then you get a Chernoff bound. The general theorem is things that are kind of sub-Gaussian. They look Gaussian-like. They have some kind of exponential-ish tail. Will give you this problem.
So, in particular, if you have this sort of exponential graph that the inequality is providing, should I sort of think of that as saying that, flip it around, the Gaussian is the largest one that satisfies it?
Yes. In fact, if you have heard the central limit theorem, this is one way of saying it. The Chernoff bounds are a way, so the central limit theorem says that if you take a bunch of appropriately defined random variables, take their average, that distribution tends towards the Gaussian distribution, right? The central limit. What it doesn't always tell you is how fast it tends towards a Gaussian distribution. The rate of convergence. This is giving you that. This is saying the precise rate of convergence is given by this table. So yes, in fact, you are saying this becomes Gaussian-like. There are bounds on the other side called anti-concentration bounds, saying that you can't get better than a Gaussian. You can't get something that's even sharper. A Gaussian is the limit. It's about as tight of a concentration as you're ever going to get, frankly. So yes, the intuition that these things all become Gaussian is an excellent intuition and is the one you should keep in your head. Because that's exactly what's going on. Any other questions? Yes?
So a lot of times we can just straight up solve for the probabilities, or are these just cases where that's really hard to do?
It's really hard to do in these cases. If you're summing up a bunch of random variables, they have different means, they have different means of their own, and you don't know how they interact with you. You know they're independent, but you don't know, it would be hard to do this in general. So that's why you have a whole collection of these Chernoff bounds that are hammers you can just apply. It's like, boom, just apply it. And again, the guide, the way to think about the Chernoff bound, again, as I emphasized, is yes, you can use it to prove a result. But it's also a guide to intuition to designing the algorithm. Because you should have the Chernoff bound in the back of your head saying, I know that if I can get any probability of success, I can then ramp it up and use a Chernoff bound average, right? So I get some answer. I don't know how good the answer is, but I know its expected value is decent. Okay, run it 100 times, take an average. I know this Chernoff bound waiting to help me somewhere. I'll get the answer. So that's how you should keep these bounds in your head, as a tool that you can use to solve the problem in an easy way and then apply the crank to make it stronger. Instead of to make it stronger all by yourself. Okay? So that's why we'll often say, we'll just design some strategy that gives me a probability of success of 1 over 10. It seems horrible, but then back of my mind is like, I know I've got my crank going. That's how we modularize our design, otherwise it gets too complicated. So, let someone else solve another piece. Question? Okay, see you on Thursday and 5 o'clock today.